All right, let's move on to the derivative of polynomials. So we're talking about, a quadratic equation, x squared plus 3x minus 5, just strings of terms separated by plus and minus, our classic polynomials. In our previous class, we found this limit, f of x plus h minus f of x divided by h as h approaches 0. And we were saying, this is finding the derivative using first principles. And it was quite a bear to put this formula into action. It always worked out, but it was very time consuming. This is the definition of derivative. If someone asks you to find something using the definition of the derivative, they want you to do the work. And recall, this is also the slope of our function at a singular point, our instantaneous rate of change, and the slope of a tangent line to a point on the graph. Never forget that. Thankfully, someone has already gone through and found a bunch of rules or formulas for us that we can use to make our life easier when we're trying to find a derivative. So these all come from that limit equation, limit as h approaches 0, all that stuff, but someone else has done it. These are all on your formula sheet. So what we're going to do is we're going to go through the various kind of simple rules and see how they play out, and then by the end we'll be able to find the derivative of a polynomial. So our first rule is the derivative of a constant. Now when we speak of a constant, we're talking about a number, any kind of number, real, whatever, but without any variable attached to it. So if you look right here on our thing, we see 14. That's a number. We see pi. That's a number. These equations happen to be y equals or f of x equals. So we know from previous classes that if we see y equals 14, that reminds us that y must always be 14. And we're looking at the graph of a horizontal line. And our equation is basically y equals a number, c. C being constant always for us. Now, the derivative of a constant is 0. And that's just our rule. So we have in the table here a few ways of expressing that. So if you have a constant within a string of terms, like if you have blah, 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 and then plus 7, the derivative of the 7 will be 0. So this is just a couple ways of putting it. dc with respect to x is 0, c prime is 0. Those are both meaning derivatives. And if our equation happens to be that y equals 14 or that f of x equals pi, then if you differentiate, the derivative of your equation will be 0. So remember, the derivative is the slope of the graph at that point, at any point on that graph. So if the slope where the derivative is 0, what does that tell us? Well, the slope of a horizontal line is 0, so this makes sense, right? The slope all along here will always be 0 because it's a horizontal line. Our second rule is a super awesome one. We use it all the time, the derivative of a power. So when we speak of a power, we're talking about a variable x raised to any exponent. So in our examples, we have y equals x squared, and then we have f of x equals negative x to the power of negative 2 or 3, which is also a power, but can be written another way. So we're going to do a lot of flipping around with this. So we look at the formula, either one, whichever is less confusing. It shows us that the derivative is going to be that number that was the exponent, and now your x will be to the power of an exponent one integer lower. So let's think about that. What is the derivative of y equals x squared? What are the moves do we have to do? We have to take the 2 and put it in the front. So we're going to have y equals 2, that's our n. And then we have x to the n minus 1. X to the 2 minus 1. So we have y prime equals 2x. This is the derivative. So what does this tell us? This tells us on the graph of the equation of y equals x squared, if I want to find the slope of any point, x equals 5, x equals negative 20, this will give it to us. When x equals 5, the slope of that at that point of the graph is 2 times 5 equals 10. I want to step back over to this one really quickly because one thing we're definitely going to have to know is our fraction math, and just kind of walk through this one. We have a bunch of examples coming up. So I move the n, the exponent, to the front, and then my math is going to be negative 2 over 3 minus 1. So just let's blow this up a bit. You need to know your fraction math. You need to know that 1 can be represented by 3 over 3. And you need to know how to do fractions, addition, subtraction, so that you can get to negative 5 over 3. So our final answer for that one would be f prime of x is equal to negative 2x to the negative 5 over 3 over 3. And there's a lot of different ways of expressing that. We'll get into it. Here come some examples. Okay, so the first one, look at your equation. Look at what's going on there. We just have a number, so this is a constant. So I know right away, without thinking, the derivative of a constant is 0. Therefore, y prime is 0. For number 2, well, this is weird. It's just an x. I didn't really talk about that. But remember, anything that's a plain x is really x to the power of 1. So if we want to think about the derivative, we're going to move the 1 in front, and we have our n minus 1. So we have 1 times x to the power 0. And remember that exponent law, where x to the power 0 is 1. So let's do it as long as possible. 1 times 1 equals 1. So the derivative of y equals x is y prime equals 1. For number 3, this is a little different. This is hard to look at. We don't know anything yet about this. Our exponents on the bottom, so rewrite. We're always rewriting in calculus to make it something that we know how to differentiate, to make our life easier, so we don't have to use first principles. So this could be written as x to the negative 4, and then I can apply that kind of power rule. So we're going to do, y prime. We're going to move the negative 4, n goes to the front. Then you just have n minus 1. The exponent steps down 1 integer. Negative 4, x to the negative 5. Now what happens if they'd asked you to express this with positive exponents only, as we often do? Then you just rearrange it. X to the negative 5 is the same as 1 over x to the 5. There we go. And to start number 4, we're going to start the same way. I don't have a rule for dealing with a radical, but I do know that a radical can be written as a fractional exponent. So let's start that way. We have our variable. Remembering the degree of the radical is the denominator of the fraction, and any powers still on it are the numerator. And then it's just straightforward power rule. Move n to the front, and then we're going to have n minus 1. So right away I'm going to write minus 3 over 3 just because I can see I'm going to run out of space. And then we have 2 over 3 x to the power of negative 5 over 3. And once again, what happens if I was, oh sorry, not 5. Ignore that. Let's erase that. That's a little bit of wishful thinking to make that into 5. Recorrect. There we go. Negative 1 over 3. T minus 3 is negative 1 still. So what happens if we're told that we have to write this with radicals and positive, or, you know, with the same kind of thing, positive exponents? Well, let's change the x, and I'll put it over here, back into a radical. So it's negative, so we can start by thinking it like this, and then we can remake it into a radical. Remember, the denominator becomes the number in the hook, the degree of the radical, and any powers, or numerator becoming the power on the variable still, it's just a 1, so we can drop it. So now let's recombine that back over here, and we're going to get 2 is in the numerator, and then we have the 3 from the fraction, and then we have a 3, a cube root, issue there? All right, so remembering these are the same, and you should be able to, at this point in your math career, move back and forth between them. At some point, we're going to get to a place where we have lots of things going on one term. We might have multiple functions multiplied by each other, divided by each other, nested within each other. So we start just making up new letters to represent that. So if we have an equation, y equals 4x squared, and we want to find the derivative of this, well, we need to think of what it's made up of. We have, a number, what we would have previously called a constant when it was multiplied, or not multiplied by anything, just sitting by itself. And we have this little kind of function here, x squared. So sometimes we like to replace x squared with u, or v, or some f, or g, and that makes our life a little easier in recognizing what's going on. So when we do that, we see that we have a constant times a function. And then we can see rule 3, which is very different than the derivative of just a plain old constant. The constant doesn't change. It doesn't become 0. We just take it along for the ride. So we have the constant, and it's multiplied by the derivative of the function, which in this case will be 4x squared. So let's do these ones. So if I wanted to find the derivative of y equals 4x squared, the 4 stays and doesn't change. And then I'm going to multiply it by the derivative of x squared. Move the 2 to the front. X to the power of 2 minus 1 is x to the power of 1. And then we end up with 8x. We can't let that constant have a derivative of 0 when it's multiplied by something else, or else it's going to make derivative of all these functions 0, which is not true. And here's another one, the second one. Now remember how to split stuff up. This is a fraction. It's your number, your coefficient, your constant, and your function is 1 over root x, which, remember, in order to use that power rule, we would want to write as x to the power of, it's a negative to bring it up, it's a square root, that's a power of 1/2. And then you would go ahead from there. So key thing here, all of them kind of the same. If you have a constant times a function with a variable, then the derivative is the constant times the derivative of the function. So let's do a couple. I'll do them a long way. So first, 3 over 2 is a number. And then we have x. Well, let's do it in lots of steps. So there's our constant, or our coefficient. There's our function. And in order to start differentiating, I want to put it in a way that is recognizable to me. So instead of writing 1 over x, I will write it with a negative exponent, x to the negative 1. And then I'm just going to apply my power rule, and remember that I don't get to mess around with the constant. So I'm doing lots and lots of steps. There's my constant, my derivative, negative 1 comes in front, negative x, negative 1 minus 1. So we're going to get 3 over 2. So many steps. You don't have to show me this many. Let's build it back up. Negative 3 over 2, because the negative is coming out in front, because that's fine. And then x to the negative 2. And if they told you positive exponents only, negative 3 over 2x squared. For number 2, before I even start, I can make my life simpler because I certainly don't know how to deal with a product, a function over a function, or sorry, a quotient, a function over a function yet. That's coming next time. So let's do a little simplifying. X to the power of 4 over x is simply x cubed, using that exponent law, 4 minus 1. So now we are going to do our constant time of function. So we're going to have 6 multiplied by the derivative of x cubed. 3 comes to the front, x to the power of 3 minus 1. There we go. And cleaning it up, multiplying the two numbers, because that's math and you can do that, 18x squared. For our last one, We've got a constant, and we've got a radical, which we're going to rewrite. So first things first, that 5 is going to be multiplied by x to the power of 3 over 4. So if I'm trying to find the derivative, g prime of x, my constant stays. My 3/4 comes to the front. Let's see if I do it correctly this time. And we're going to have n minus 1. And if we're talking quarters, 1 is 4 over 4. So we have 5 onto 3/4 x to the power of negative 1/4. So let's do this with radicals or positive exponents. So 5 times 3 is 15, goes on the top. 4 goes on the bottom. The exponent on the x is negative, so we're looking to the bottom. It's fractional, so we're going to have a degree for root x to the power of 1. This is the last thing we need to do to find those polynomial derivatives. So derivative of a sum or difference. So this basically means that if you have a string of 4x squared plus 3x minus 17x cubed, you can differentiate each chunk individually. So we see an example here. We have y equals x squared plus 7x. Well, let's, we like to rename our functions as something else. So we have a u and a v, an f and a g, whatever. But we can do it separately. So if we were to do this, y prime, the derivative of x squared is 2x, moving quickly now. And the derivative of 7x is 7. Done. And you can do that in chunks. Now, watch out for things like this question, where you see a multiplication. We didn't learn anything of the product rule yet. So instead of dealing with the multiplication, a product rule, something complicated, rewrite our equation. Distribute. Make this a polynomial with 3 terms. So we're going to have f of x is equal to 4x cubed minus 5x squared plus x, and I'm rewriting as I go, over 2 times x to the power of 1/2. That's at root x. And within that last term, the first two would be easy. I'm just rewriting the polynomial. I'm not differentiating. X over x to the 1/2. This is an exponent law, quotients, where you subtract the numerator exponent from the denominator exponent from the numerator exponent, pardon me. And we can rewrite that third term as x to the power of 1/2 over 2. And now we can just use all 3 of these terms. Would use that rule number 3, that constant multiplied by a function to differentiate. And here they are, all written in fancy pants writing, formula sheet writing, so just make sure you get that. And we'll end this lecture by differentiating 3 examples, all of which will work just fine with what we've learned on the previous slides. So starting with number 1, a little bit of a rewrite maybe first, so that things have exponents and look like things we know about, plus 6 times x to the power of 1/2. And then we're just going to differentiate term by term. So here, the exponent is 8. It's going to come out in front. And I'm building it in, and then I'm going to drop down from an 8 to a 7, 8 minus 1. And then likewise in the second one, the exponent is 1/2. That's going to come out. That's 6 times 1/2. And we're going to have 1/2 minus 2 over 2, which is x to the negative 1/2. Finally, we're going to clean this up because we have a lot of things that can be reduced and made to look nicer. F prime of x is going to be equal to negative 2, negative 8 divided by 4, x 7 plus 3, and then x to the negative 1/2 brings it down to the denominator. The fractional makes it back into root x. Done. Make a little line here. For number 2, once again, it's multiplication. I don't want to deal with that, so I'm going to turn it into something I recognize, or a string, a polynomial, like a string of terms, by using FOIL or expansion, binomial expansion. So first, cleaning up. We get 6x squared for first, minus 15x plus 2x gives me minus 13x, and this should be familiar from last term, minus 5. And then very, very straightforward. To find the derivative, the 2 moves into the front, it multiplies by the 6. The x squared becomes an x, drop down a degree. For the negative 13, the invisible 1 moves into the front, doesn't change anything. Becomes x to the power 0, which is 1. And for the negative 5, this is a constant, and the derivative of a constant is 0, so this is our answer. Another trick that I really like is, once again, we haven't done anything about, quotient rules and dealing with that. So we're going to, instead of bringing things together like we did in number 2, we're going to break things apart and see what that does for us. So rewriting, remembering that if you have a string of terms in the numerator, you can break it apart. And maybe I'll even at the same time write this as x to the power of 1/3, all on top of the same denominator. Now I'm going to use exponent laws to make it so I only have one variable. So x squared over x5 is the same as x to the power of 2 minus 5, x to the power of negative 3. This one's a little uglier. Maybe I'll break it off up here. I need to do 1/3 minus 5. Now remembering, if I want to change 5 into a number over 3, it's going to be 5 times 3, 15 over 3 is the same as 5 when you express it as a fraction. So 1 minus 15, negative 14 over 3. Not pretty, but gets us to one to one variable. X to the power of negative 14 over 3. Okay, so let's differentiate. Pull the negative 3 in front and drop it down a degree. Negative 3 minus 1 is negative 4. Don't mess up your negatives. And for this one, I'm going to leave some brackets because we're going to pull negative 14 over 3 in front. And then we have x to the power of negative 14 over 3 minus 1, which is minus 3 over 3. So we get negative 17 over 3. Cleaning up a bit. First term is fine. Oh no, we could put that. Let's back that up a bit. Let's make that negative 3 over x to the power of 4. Get rid of our negative exponents. We have a negative and a negative, so we're going to have a plus sign here. 14 in the numerator, 3 in the denominator from the coefficient or the constant, and then we have a negative exponent, so we know that the x will be in the bottom, and it's also fractional, so we know it'll be, the denominator goes in the hook, and the power, the numerator stays with the x. Done and done.